Please join me in welcoming to the Distinctive Voices podium, Dr. Alan Nathan.
Thanks very much, Susan, for the introduction and, of course, for the invitation to come here to this beautiful spot and talk about something that I'm quite passionate about, which is the intersection of physics and baseball. So how could you not be excited about baseball when you see a picture like this, which actually appeared in our local newspaper in Champaign, Illinois? This is a remarkable photo. It's very hard to get a photo like this because you see the ball and the bat are in contact with each other. It's a real photo of opportunity. Okay, well, look, let me just tell you very, very briefly about myself. Susan already mentioned a few things. In my day job, I'm an experimental nuclear particle physicist, and in that job I look at high-speed collisions between subatomic particles. But I moonlight doing physics of baseball research, looking at a very different kind of collision, a high-speed collision between a baseball and a bat. Now, remarkably, even though the scale is very, very different in terms of how fast things are going, in terms of how big things are, a lot of the same physics that applies here also applies here. And one of the things physicists love to do is look at the connectedness among things, okay? You know, the conservation of momentum and energy applies here, and it also applies here. So that's part of the reason why I get excited when I do work in this area. That, of course, in addition to being a baseball fan, a big baseball fan. In fact, I've been a baseball fan I see someone with a Red Sox shirt back there. I got one too. I've been a baseball fan longer than I've been interested in physics. So, and that's a long time. So there are many similarities, and of course the real thing is I get to watch and play baseball and call it doing work, okay? So this is really a true intersection of passions. So now, just to tell you very briefly, and I hope you can appreciate this, the connection between physics and baseball. This is a picture known probably to most baseball fans. It's the 1927 New York Yankee team. That's the year that Babe Ruth hit 60 home runs. Many people consider this the greatest baseball team ever assembled. Now have a look at this. This is the 1927 Solvay Conference. Many people consider this the greatest physics team ever assembled. And of course, recognizable faces, you know, Babe Ruth, Albert Einstein, the most valuable players of these teams. Okay, well, so those of you who are interested to learn more about it, this is how I got started. I read this book in its first edition. This is the third and probably final edition, written by Bob Adair, who's a retired professor of physics, very similar background to mine. Oh, he's a bit older than me. He's from Yale, and it's an interesting story about how he ended up writing this book, but I won't bother to tell it. But this is how I got started. Some very interesting things from this book. Let me just quote you a few things. Because this is a remarkable book because it gives you, it's a book written, you know, it's about baseball, it's about physics and the intersection between them, but it really gives you a good sense of how a physicist goes about thinking about not the physics of the kind of research they're doing for a living, but the physics of the everyday world where things aren't always so simple. So here's a nice quote. The physics of baseball is not the clean, well-defined physics of fundamental matters. Hence, conclusions must depend on approximations and estimates, but estimates are part of the physicist's repertoire. So one of the things that physicists learn how to do from an early age is how to estimate things. There's a whole class of problems that are known as Fermi problems. Fermi was a genius at knowing how to estimate things. So that's part of what you have to do. Things are not so nice and clean as they teach you in the textbooks. You have to make estimates. And usually that means you have to create a model of the situation. Okay? Now, people oftentimes ask me, you know, am I going to become a better player for, you know, having read this book? And, of course, the answer is no. You're not going to become a better player. I'll have more to say about that later in the talk. The goal of studying the physics of baseball is not to make a better player. The players know that, you know, the game has evolved for 150 years. The players know through whatever means, trial and error, you know, whatever, they know how to play the game. Our goal is to try to understand lay some physics basis for what they already know. So I don't believe people will become better ball players for having done this, and that it for sure isn't the goal of the whole thing. Here's a nice little quote from Bob Adair. The physics of baseball is not rocket science. It's much harder. Okay? True enough. It really is true. Finally, as I said, you have to make estimates. You create a model, and then you try to adjust the parameters of that model by doing experiments. Now, some of the experiments you can do in the lab, but the big laboratory is the game itself. And whatever model the physicist creates for the game, it has to fit the game. Okay? The physicist model of the game must fit the game. So these are just words of wisdom from Bob Adair. Here's my own website that you're free to go to. It's kind of out of date now. You see the last time I updated it was over a year ago. But I try to put things on there that interest me and put links to things, and some people have found it useful. All right, topics that I'm going to cover. I'm going to cover the two main things that actually Susan mentioned in her introduction. The physics of the ball-bat collision. How does a baseball bat work? What's the deal with wood bats versus aluminum bats? How does a batter put spin on the ball by batting it? So I'll talk about those things. And then I'm going to talk about the flight of the baseball. Drag and lift and all that. And I want to especially spend a little bit of time towards the end talking about some new tools that have only become available in the last couple of years to study trajectories of baseballs. And I want to apply it to a certain particular problem that's of interest to a lot of people, namely, how far did that home run really go? Okay. All right. So now, Yogi said you can observe a lot by watching. So I invite you to watch. And a couple of things. First of all, here's another remarkable photo from the Daily Illini. That's the student newspaper. This is a student-taken picture. This is a women's softball player. And again, the ball has just barely left the bat. You can see the bat is bent a little bit. Okay, now let me show you. So that's one of the things that can happen. I want you to look at this picture down here. This is taken at 30,000 frames per second. It shows a ball at about 120 miles an hour inserted on a flat plate. And notice how that ball becomes totally squashed as it's hitting the plate. It really squashes by a lot. And then it bounces back, and if you can just sort of count frames, you can see that it bounces back at a slower speed than it comes in. A lot of energy is lost in that collision. Now look at this. This is a high-speed video of a softball player swinging a bat. And so wait till it recycles again. I'll point out a couple of things. First of all, you could probably learn a lot about the swing by watching this guy. Now watch when the ball hits the bat. Notice how much the bat slows down right after that. Boom. See, the bat slows down a lot. That's conservation of momentum. The bat transferred momentum to the ball in the forward direction, and so the ball, therefore, had to transfer an equal amount of momentum to the bat in the opposite direction, so it tends to slow the bat down. So again, as Yogi says, you can learn a lot by watching. All right, so let's talk about that brief instant of time when ash meets cowhide, when the ball and bat meet. So this is the part of the game of baseball that originally got me interested in the physics of it, is studying just this very thing. All right. First of all, the forces are very large and the time of the collision is very short, and those two things are related to each other. The forces are large because the time is short. So, a ball's coming in, let's say at 90 miles an hour, and it goes out at, roughly speaking, 90 miles an hour. So, in order to turn that ball around in a very, very short amount of time, that requires the acceleration to be large, which means, from Newton's laws, that the forces have to be large. So the collision time is something like 1,000th of a second, a millisecond. Okay, that's a very small amount of time, and the forces required to turn that ball around reach into the thousands of pounds, 8 to 10,000 pounds peak forces. So the forces are very large, considerably larger than the amount of force that a batter can actually apply to the bat. Okay? It's not the batter who's supplying that force. It's the speed of the bat. It's essentially the momentum of the bat that's doing it. Now, during that time, the ball compresses, sort of like a spring, squashes down. You saw the picture before. and then it expands back out again. So the way a physicist would try to think about these things sort of from an energy point of view is the ball initially has kinetic energy, energy of motion, and it compresses like a spring, converting that potential energy kinetic energy into potential energy. Okay? The ball comes to a momentary halt, as it must do if it's going to turn around, and then it expands back out again, converting the potential energy back into kinetic energy. But it's and in the process, the bat recoils backwards. Well, it doesn't, if the bat were initially at rest, it would recoil backwards. So in fact, what actually happens is the bat just slows down, as we saw in the previous video. Now, this is a very inefficient process. The process whereby the ball compresses and expands back out again is very, very inefficient. A lot of energy is lost. In fact, if you were to whack this ball really hard, okay, and then retrieve the ball, and you could hold it up to your cheek, which is very sensitive to temperature, and you could figure out where the ball and bat met, where on the ball, just by feeling that little bit of rise in temperature. The temperature goes up. The ball, after you whack the ball a few dozen times or maybe less, the ball starts to get deformed, it gets soft. Okay, they throw them out of the game if it has any blemish on it at all. All that took energy, and that energy largely came from this process of compressing and expanding back again. So one of the crucial things to understand about the ball-bat collision is how inefficient it really is. So most of the energy. So there's this thing called the coefficient of restitution. I'll talk more about that later. That is sort of a measure of how elastic that ball is. When the coefficient of restitution is high, less energy is lost. When it's low, more energy is lost. And the energy mostly goes into heating up the ball or deforming the ball. Some of the energy, and this plays a crucial part in some of the things that I'll talk about, goes into making the bat vibrate. When the ball doesn't hit the bat right on the sweet spot, we'll talk about that too, the bat vibrates. You can feel it in your hands. It hurts. Okay, it stings. Sometimes the bat breaks. That is energy that gets transferred to the bat by the ball that otherwise would have gone back into the ball. So it's another inefficiency in the collision. Now, to hit a home run, what's required? You want a very high batted ball speed. Okay? Typically, if a batted ball speed is something like 105 miles an hour, more or less, and the ball is otherwise optimally hit at the optimum angle, which is sort of 30 to 35 degrees. In Physics 101 is 45 degrees, but because there's air drag and things like that, it's actually at a bit lower angle. And with lots of backspin, that ball will travel about 400 feet. And it's a pretty good rule of thumb. The 400 feet is the canonical long home run, okay? A 400-foot home run a 400-foot fly ball will mostly get you a home run unless you're hitting in the deepest part of the ballpark. Each additional mile per hour batted ball speed will give you another somewhere between 5 and 6 feet. So you can see that batted ball speed is all important in order to get a long fly ball. So then one can ask the question, what determines the batted ball speed? Batted ball speed is of crucial importance in getting a long fly ball, getting a home run. And since the home run is probably the most exciting play in baseball, let's talk about home runs. What determines batted ball speed? Well, basically there are three generic things that determine the batted ball speed. The speed that the ball is being pitched, the speed with which the bat is being swung, and then some property of the ball-bat collision that I want to simply call the collision efficiency. It's a joint property of the ball and the bat that sort of measures how efficient the bat is at transferring energy to the ball. So the only formula you're going to see in this talk, okay, is this one here. Batted ball speed, BBS, is equal to some number, this is that collision efficiency, times the pitch speed, plus 1 plus the same number times the bat speed. This is the only formula I'm going to show you. It's a very simple formula. And so, and Q is that collision efficiency. Now let me just give you some very typical numbers. For when the ball hits the bat on a wood bat, right near the sweet spot of the bat, it's a spot maybe 5 or 6 inches in from the tip. Okay, thanks to whoever brought this for me. Hard to bring those on an airplane these days, as you know. I have tried, but all right. This number is about 0.2. That's sort of a measure of how inefficient that collision was. If the bat were infinitely heavy and the ball were a super ball, this would be 1. You see, it's only 20% of that. It's a very inefficient collision. And so 1 plus Q is 1.2. So, by the way, what you should note is this is quite remarkable. You see, the number that appears in front of the bat speed is 1 plus this small number, and this is the small number. So you see that in determining the batted ball speed, bat speed is much, much more important than pitch speed. Okay? So, for example, plug in some numbers. If you have a 90 mile per hour pitch speed, this is sort of typical, 70 mile per hour bat speed, which is sort of typical, maybe it's a bit on the high side, that will give you the 102 miles an hour, close to what you need to hit a 400-foot home run. But notice, though, that this term matters much more than this term because of this 1 here, okay? And the 1, if you examine it in detail, the 1 arises because the bat is already going in the direction that you want the outgoing ball to go. That's exactly where that 1 comes from. So each mile per hour of bat speed is worth about another 6 feet on a long fly ball. Each mile per hour of pitch speed is only worth about 1 foot. So people oftentimes ask, what's more important, bat speed or pitch speed? Well, it's clearly bat speed. But if you think about it a bit, you really know that already, okay? For example, you know that you could hit a fungo. What's hitting a fungo? Fungo is something where you toss the ball up and you hit it like that. There's no pitch speed whatsoever, right? And you know you could hit the ball quite a long ways as a fungo. Now you could ask the question, all right, suppose I try to bunt the ball. Okay, I just let the ball hit the bat with the bat not moving. You know the ball's not going to go very far. So everyone who's thought about it a bit realizes that bat speed is much more important. But you may not have realized how big an asymmetry it really is, sort of a factor of 6. Okay? All right, so now we're asking what makes the batted ball speed large. So the pitch speed and the bat speed make it large, okay? But let's focus in on this collision efficiency. So this is getting really down to the nitty-gritty. This is the stuff where you could do some real research on this, okay? So here's the formula again, same formula. Remember I said I was only going to show you one formula. I may show it to you more than once, but all right. So what does Q depend on? So the first thing that Q depends on is the weight of the bat in the barrel of the bat. It has another name for those of you who know about these things called the moment of inertia, about a point near the handle. So it's a measure not only of the weight of the bat, but how that weight is distributed. And so when a large fraction of the weight is distributed in the barrel of the bat, far from the hands, the moment of inertia is large. And so, think of the ball incident upon the bat. If the bat is very, very heavy, if it's got a lot of weight back here, it's not going to recoil very much. Okay? Whereas if it's light, it can recoil a lot. When it recoils, it takes energy away from the ball. So the heavier the bat is, and heavier in the qualified sense, now that I'm saying, heavier in the barrel where it matters, that collision efficiency is going to be higher. And again, it makes sense. I mean, you can hit you can hit a ball harder with with something like a 20-pound steel pipe than you can with a wooden ruler. Okay. So and that's really all there is to it. It really has to do with how much weight there is behind the collision. Sometimes it's called a swing weight. It's called a swing weight because the amount of weight in the barrel also determines how fast the batter can swing the bat. Okay, so let's go on. So a heavier bat's going to be more efficient, less recoil, and therefore a larger Q. I could show you a formula, but you don't need formulas for that. All you have to do is know that the heavier the bat is, the larger that efficiency is going to be. But the bat also has to be swung. And generally speaking, the heavier the bat is in the barrel of the bat, the less rapidly the batter is going to be able to swing it, the lower the bat speed is going to be. And so then that raises a question. There's obviously some trade-off. If I make a bat heavier, I'm going to get a higher collision efficiency, but I'm not going to be able to swing it as fast. If I make it lighter, I'm going to get a lower collision efficiency, but I'm going to be able to swing it faster. So obviously there's a trade-off, and that leads to the notion that for everybody there must be some sort of ideal bat weight. Okay? What is the ideal bat weight? Well, it's easy. It's just a matter of simple physics to calculate the effect of the bat weight or the moment of inertia on this collision efficiency. Okay, that's a very easy thing to do. This part of it is much harder. That's not just physics. That's physiology, biomechanics, and things like that I don't know a whole lot about. But some people in the audience probably do. Okay. So nevertheless, you could sort of treat it as an experimental kind of science. Namely, you can measure on a given batter how his bat speed depends on the moment of inertia of the bat, and then from that process find an optimum bat for him. Okay? And some people try to do that, actually. Now, batters have been known to do something that's considered illegal, which is to cork the bat. Okay, what is corking the bat? Well, there's a picture up here, there's sort of a little cartoon that shows you. So the idea behind corking a bat is you want to reduce the weight of the bat in the barrel of the bat. Now, you could do it by making the barrel smaller diameter, but you lose hitting surface if you do that. So what you do is you drill a hole through the center, maybe an inch in diameter, maybe 10 or 12 inches deep. Okay, and then you backfill it with cork, and the cork serves no useful purpose whatsoever except to disguise this illegal act of yours. Okay, and then they paint over it and everything. Now, batters do this because of their belief that the trade-off between when you do this, you lower the collision efficiency, but you raise the bat speed. So they do this under the belief that that trade-off is in their favor, that they don't lose as much in collision efficiency as they gain in bat speed. So, of course, Sammy Sosa those who remember these things, back in June of 2003, got caught. Here's his cork bat broken, and it was inspected, and anyway. And my phone didn't stop ringing for 2 days, talking with reporters. It was one of the fun times I've had. Now, all right. Now, based on my study of this whole thing, I concluded that if your goal in life is to get a longer fly ball, that this trade-off is not in your favor. Okay? You're better off filling it with lead rather than filling it with cork. You're better off making it heavier, not lighter. And that's the way the trade-off works for most batters. So you may ask, well, why do they do that then? They're not going to get a longer fly ball. And the reason why they do that is because bat speed is not the only thing that's important. Bat quickness, and when batters talk about bat quickness, I assume they're talking about the acceleration of the bat. Not how fast it's going when it hits the ball, but how rapidly they can get it from here to here, from where it starts to where you want it to be in the shortest time possible. The shorter you can make that time, the longer you can wait on a pitch. The longer you can wait on a pitch, the more you can observe what it's doing. The lighter the bat is, the more easily you can change your swing after you've already begun your swing and make adjustments, pulling the bat in on an inside pitch or reaching on an outside pitch or whatever. So if you're trying to hit for average, a high batting average, or if you're trying to make contact more often, then I think corking the bat really does help. If you're trying to get the longest distance possible, I'm pretty convinced that it doesn't. Okay. What else does Q depend on? It depends on the bounciness of the ball. This is that coefficient of restitution I told you about. Now, I'm going to just drop this ball, and you see this ball is not particularly bouncy. If this were a hard surface, completely hard surface, and I bounced it, it would come up to about 25% of its initial height, meaning that 75% of the energy is lost. The coefficient of restitution is just the square root of that, so it's a number that's about 0.5 for a baseball. It's a number that's legislated at Major League Baseball. There's a certain range it has to fall. Balls are tested, it has to fall within a certain range. So this is show you different balls. Here's a super ball, and here's a baseball, and whatever. Okay. Is the ball juiced? This is a question that comes up periodically. It's actually come up this year. The last time it came up was the year 2000, in which the number of home runs hit during the months of April and May, were inordinately higher than they were the previous years. And so people wondered, is the baseball juiced? And what does that mean, is the baseball juiced? Means, is its coefficient of restitution larger now than it was last year or 10 years ago or whatever? Okay? It's something under the control of the manufacturers. Well, when this came up and it's come up again this year because people who do this stuff in a serious way, and they're just ordinary people, they're not scientists or anything, they're just people who love the game of baseball and have a lot of time on their hands, evidently, and they analyze these things. And they have looked at the average distance of home runs that have been hit this year, and they've discovered that so far in the season's only 2.5 weeks old, it's about, but there's already been, 350 home runs or something like that. And so enough that you could start taking averages. The average fly ball, average home run distance is about 8 feet longer than it was a year ago in the last several years. So they were wondering, is the ball juiced? Well, actually, let's see. I thought I had, hold on a second here. I thought I had another slide, but I don't see it. Where did I put it? Hold on. Is it here? Nope. All right. I thought I had a slide that I added right at the last minute, but I can just tell you about, no, this is the slide. Somehow it slipped over it. All right, but here it is. All right. So, does anyone know the name Charlie Finley? Former owner of the Oakland A's? Several years ago, I got an email from Charlie Finley's niece. It's a woman basically my age. Her father was Charlie Finley's brother. Her father had just passed away. She was clearing out his estate and everything, and she found boxes of unopened boxes of baseballs from the late 1970s. Wouldn't it be a nice idea to test these baseballs against current baseballs, which was actually in 2004? So, sure, send them to me. So she sent them to me. And so I did this experiment. Fire a ball out of a cannon at 120 miles an hour. Measure the rebound velocity. So the coefficient of restitution is, I had it hit a steel wall. It's just the ratio of the outgoing to the incoming speed. Okay, so it's a number. I remember I told you it was about 0.5. Okay, so for this collection of balls, it was about 0.46, 0.47. Here are 6 baseballs that I bought brand new from Rawlings, 2004 balls. They all had a coefficient of restitution a little bit under 0.47, something like that. Now, there was a lot more scatter in the balls from the 1970s, but on the average, you would say that they weren't all that different from each other. Okay, there was a much more scatter, but on the average, they weren't that much different from each other. Now, what you can make of that what you will. Of course, the sample size is small. If anything, you might have thought that even though the boxes were unopened boxes, they were in their original packing material, the balls might have deteriorated. In fact, they had. Both sets of balls were put in a humidor and kept at a constant temperature and 50% humidity for about 3 weeks prior to the test, so they were all under the same conditions. But there was no evidence that that the 2004 ball had a higher coefficient of restitution than the 1975 to 80 ball. We couldn't figure out the year exactly, but we have it nailed down to that 5-year period. Anyway, it's something amusing that I did with my time. So they were equal to within a few percent. And what I would like to actually see done is a regular procedure where, you take a few dozen baseballs every year and you do exactly this kind of test and then you just stash it away. It's very hard after the fact to do that because it's very hard to find old baseballs that haven't been used. Once they're used, you really can't do the test on them because they may have changed. Okay. Now, what else does Q depend on? It depends on the location on the bat where the impact occurred. Now, there are 3 different things. This you've seen already. This is an impact right at the sweet spot. Here's an impact outside of the sweet spot, near the tip of the barrel. Here's an impact closer to the handle. Okay? Now, watch that bat vibrate. Okay. Now, truth be known, these were special bats that may be a little bit more flexible. But nevertheless, it almost gets knocked out of his hand. It's vibrating so much. Okay? So now you can do this test at home. All right? It's not dangerous. Okay, you can, so now some of you're not going to hear this too well, but try it yourself anyway. Hold the bat very lightly, maybe 6 inches down from the knob, and then just take a baseball, okay, and just hit it. Whoops. Now, I can hear this vibrate, and I can feel it vibrate. Now, you might not be able to hear it, but okay. Okay, now do the following. Now start here, and then just slowly work your way to the end. Notice here, it's still vibrating, but it's a much higher frequency. The fundamental vibrational amplitude has what is called a node, right around 6 or 7 inches in from the end. Okay, that's the place where when you hit it, you don't feel a thing in your hands. It feels perfectly smooth, and basically the bat's not vibrating. So, and if you hit it outside of that spot, you're going to transfer energy to the ball will transfer energy to the bat in the form of vibrations. It'll hurt, it'll sting, the bat may break, and the ball won't go as far. Simply because it has, that energy that got transferred to vibrations is energy that the ball didn't have after the collision. Okay, but these pictures are quite remarkable, showing the bat almost leaving his hands. Okay, so here's a little cartoony thing. You could talk about a sweet spot, and there are different vibrational modes, just like you could pluck a guitar string and you've got different modes of vibration. And the one that we were just feeling by hitting the bat was the lowest vibrational mode. It's got a node, meaning a place where it doesn't vibrate, maybe 6 or 7 inches in. The second mode of vibration is a little bit more complicated, and it's got a node a little bit closer to the tip, and somewhere between the two is sort of the ideal hitting location. So that's another thing that the batted ball speed depends on. One interesting thing. So here's the shape. This is what the lowest vibrational mode looked like. It's sort of vibrating about these two fixed points. Those are the nodes. Okay, and notice when a bat breaks, oftentimes you see here the bat hit on the inside, and notice that it's cracking towards the catcher. Okay, here the ball hit on the outside, and it's cracking towards the pitcher. And you can understand that entirely from this picture here. When the bat hits, when the blue ball here is hitting on the outside, the bat bends this way, it bulges in the middle, okay, and so it's going to crack towards the pitcher. When the ball hits here, it bows out this way, and it's going to crack towards the catcher. And that's exactly what you see. So pay attention to that next time you see broken bats, and there's lots of opportunities to see broken bats. They're breaking like crazy. Okay. Now, let's talk about wood versus aluminum. Does aluminum outperform wood? So let's try to answer that question scientifically. So an aluminum bat is a hollow bat. Okay, it's unlike a wood bat, which is a solid piece of wood. An aluminum bat, or in general non-wood bats, are hollow bats. It's a thin shell. So necessarily, there's compared to a wood bat, less of the weight of the bat is in the barrel of the bat. It's more uniformly distributed. So for a given weight, the moment of inertia about the handle, the thing I call the swing weight, the thing that determines how rapidly you could swing the bat, it's going to be less for aluminum than for wood. That's a disadvantage for aluminum. Okay. It's going to have a smaller Q because of that, smaller collision efficiency because there's just less weight behind the collision. But the batter is going to be able to swing the bat faster. And so those two things trade off against each other in a manner that we talked about already. Okay? For the most part, those two effects just sort of cancel out and you don't have any net effect. So why do batters seem to prefer to use aluminum bats given the opportunity? Has nothing to do with this at all. Okay, what it has to do with is what are called hoop modes. And the hoop mode is a mode. I should have thought to bring wait a minute. Okay, I could use this. Imagine that this is hollow, it's filled with water, but you see that this thing compresses, okay, when I press it. In fact, this is exactly what a hoop mode is. So when the ball hits this, you get this mode like this, okay? In fact, this particular mode of oscillation is not a bending mode like I showed you for wooden bats. A bending mode is like this. This is a compressional mode, okay? And that mode doesn't exist for a wood bat. A wood bat is almost, since it's solid, it's completely incompressible, okay? But it is there for an aluminum bat. It's that mode, that vibrational mode, that is responsible for the ping that you hear when a ball hits an aluminum bat, okay? And this is what is known as the trampoline effect. And I want to and so the answer is yes, aluminum outperforms wood, and it's because of this trampoline effect. I wanted to show you, I have a slide, but I'm going to skip the slide, and I'll get to that in a second. Forget about the slide. So I have an example of the trampoline effect. So I have in my hand two seemingly identical little black balls here, okay? They feel the same, they look the same. Now, what I need to do is bounce them, show you they're not the same. This one is totally dead. It hits a hard surface and it dies. This one is basically a super ball. Okay? All right? So, that's my wood bat. This ball is totally dead off of a wood bat. This is a super ball off the wood bat. Now, instead, let me take each of the balls. Here they are. Okay? And I don't even know which one is which anymore, but I'm going to have it hit my little bongo paddle. My bongo paddle is just a thin plastic membrane stretched on this, okay? And there's one of them. There's the other one. They both bounce virtually the same on that. So what's going on here? Well, what's going on is that when the ball hits a wood bat, basically all of that energy goes into compressing the ball because the bat itself can't compress. But when the ball hits an aluminum bat, that thin shell can compress, okay, so that not all of that energy gets taken up by compressing the ball, which is very, very inefficient. Instead, it compresses the bat, and that's a very efficiently returned. And this is an extreme case of it. In this case, when I hit this wood here, this wood is completely incompressible. All of the energy went into compressing the ball. When I hit the bongo paddle, none of the energy went into compressing the ball. It all went, because this is much more flexible than this, and all went into compressing this, and that's what the trampoline effect is all about. And that is why aluminum bats are so much better than wood bats. Okay, so some additional remarks about Q. First of all, it can be measured, this collision efficiency. Now watch this. Here's a high-speed video here. It's not so high speed. Okay, it should recycle. Okay, the ball is being shot out of a cannon onto a bat. Here you can see the bat recoiling. So the ball passes through these speed gates, these beams of light, and it breaks the beam of light, and by knowing the distance between these, you can measure the speed of the ball going in, the speed of the ball going out, and the ratio of those two is exactly what Q is. Okay, so you can measure that, and people do measure that, and they use that as one of the ways to regulate the performance of non-wood bats, which organizations like the NCAA or the Amateur Softball Association, in order to preserve the integrity of the game or whatever other reason, prevent injuries or whatever, due to a high batted ball speed, they want to regulate the performance of bats. And this is how they do it. So, Now, you may ask, what does doing an experiment like this have to do with what happens in the field? After all, notice that this bat is being held in a clamp over here that's free to pivot. Well, that's not exactly the way a batter holds the bat. A batter has a considerably looser grip. So what does this experiment have at all to do with what goes on in the field? Well, this is one of the most interesting things that I learned about early on when studying the physics of baseball. So the point is that, you could do the following experiment. Hit the bat at the barrel, measure the movement of the bat at the handle. Okay? When you do that, this is what you find. At time t = 0, you hit the bat somewhere in the barrel of the bat, and then you measure the movement of the bat. okay, with accelerometers, just little sensors that allow you to measure something with high speed. So, if the ball hits here, the bat starts to rotate, okay? Now, the important thing is this, though. You could do all these measurements, but the important thing, you can even see the vibrations. The important thing is the following. Notice that the handle of the bat moves a noticeable time after the bat was struck on the other end. The bat is not a rigid body on this very, very short time scale. If I hit one end, the other end does not immediately move. It takes time for it to move. Okay? Therefore, and in fact, by the time this is a half a millisecond. That's 1 millisecond. You see, the bat doesn't even begin to move until about a bit more than a half a millisecond after the barrel of the bat was hit. By then, the ball has pretty much already left the bat. So nothing at the end of the bat could possibly matter. Nothing at the handle end of the bat could possibly matter as far as the ball is concerned out here. Okay, so nothing could matter. So how tightly you're gripping it, whether it's free, totally free, or being gripped hard or weak or whatever, the hands, who's holding it, whether it's a big guy that's holding it or a little person that's holding it, none of that matters. As a matter of fact, the batter, once the bat is sort of right at the right location, just about to meet the ball, the batter could just as well let go of the bat, and it wouldn't make a bit of difference as far as how far the ball goes. It's true. And a lot of people don't believe it. But it's true. Okay. And there is lots of experimental data that support that. I mean, this is just not just sort of a pencil neck geek physicist or something. Okay. It really is true. Confirmed experimentally. So the batter could just as well drop the bat before contact. It would have no effect on the ball. Of course, it would have an effect on the bat, but not on the ball. All right. So let me switch gears, and in my remaining however much time, I'll talk about the aerodynamics. So here's a cute little pictures I grabbed off the web. And so the way a physicist would approach talking about this subject is to talk about the forces on the ball. It's the forces that determine the trajectory. So a ball that's flying through the air has 3 forces on it, one of which everyone is familiar with. It's just gravity, the weight of the ball, which is always pulling it down. There's also the drag, the air drag, which is slowing the ball down. So this is because the ball is, if you like, is colliding with air molecules. It has to push the air out of the way. And that always tends to slow the ball down. The direction of the drag force is always exactly opposite to whichever direction the ball is moving. Now, the third force is what is known as the Magnus force. It's the force on a spinning baseball. Okay? And so if the ball is spinning around like this, okay, then the direction of that force is if you look at the direction, so the ball is headed off this way. That's the direction of the velocity. The ball is turning, the leading edge of the ball is right here, and it's turning in that direction. That's the direction of the force. If you want to know the direction of the Magnus force, the force responsible for a curving ball, it's in the direction that the leading edge of the ball is turning. Okay. So, now, in Physics 101, we always say, neglecting air resistance, calculate, okay. Well, I want to show you that doesn't work very well for a real baseball. Okay, so a real trajectory versus a Physics 101 trajectory. If I hit a ball with an initial takeoff angle, I think I did this about 30 or 35 degrees, 100 miles an hour, if I only put in the force of gravity, this is just a calculation, of course. If I just put in the force of gravity, the ball would travel well over 600 feet. Okay, and no ball in existence has ever been hit that far. Okay, so we know that air resistance, air drag must matter a lot. So if I turn the drag back on again in the nice thing about the calculation, I can turn the drag on and off and see what the effect is. You see the effect is almost a factor of 2. The ball that in the absence of drag would go over 600 feet would go only about 350 feet when you have drag. So that's a big effect. So this approximation that you do in Physics 101, it's not a good approximation for a baseball. Now, it is not often appreciated that we know the effect on a long fly ball, that shows you that, but it also affects a pitch baseball. A pitch baseball loses about 10% of its speed between when the pitcher releases it and when it crosses home plate, about 60 feet, 55 to 60 feet. So, the ball is going to lose something between 8 and 10 miles an hour. That's a lot. So the ball that is, comes out of the pitcher's hands at 95 miles an hour is only crossing the plate around 85 miles an hour. Okay? So when they tell you, the radar gun, okay, the speed of the pitch, what speed are they telling you? They're probably telling you something that's very close to where the ball was released. But if you were to measure it, and it's been measured carefully with this pitch FX system that I'll tell you about shortly, it would be a lot slower when it crosses home plate. This trajectory without drag is a perfect parabola here, you see, all right? It's perfectly symmetric about its apex. But real baseballs, not only don't real baseballs do that, players know that real baseballs don't do that. So because of drag, the ball covers much more territory. It goes farther on its way up than it does on its way down because it's slowing down, okay, every bit of the way. And outfielders know this. Outfielders, when they settle under a fly ball, the ball reaches its apex and then it seems to drop almost straight down. Well, it doesn't really drop straight down, but it really drops down at a much steeper angle than it rises up. Okay? And again, people who play the game may not know what an apex is but they certainly know the way the ball goes. Maybe they do know what an apex is. All right. And the optimal angle, I mentioned this already, is 45 degrees if you're in a vacuum, but it's more like 30 or 35 degrees when the ball is going through the air. Okay, some effects of spin. All right. Typically a fastball, the classic four-seam fastball, it's thrown like this. So it's going that way, and it has backspin on it. Most pitches have backspin on it. So the leading edge of the ball is going up, okay? So there is an upward Magnus force, which opposes gravity. And that gives rise to what is known as the hop of the fastball. People ask the question, can a fastball actually rise? Well, in principle, a fastball could rise if you could put enough spin on it so that the upward Magnus force would be larger than the downward force of gravity. But in practice, a human being probably can't do that. So there's no evidence that a baseball could rise. You could take a styrofoam ball, something much lighter than a baseball, but the same size as a baseball, and throw it with a lot of backspin, and you can make it rise. But that's because the force of gravity is so much smaller for something light like a styrofoam ball. So the hop of the fastball. The other thing is that batters who are trying to get the longest fly ball possible will undercut the ball. They'll hit the ball below the center of gravity of the ball in order to, because of the friction between the ball and the bat, will try to get backspin on it. The backspin gives you an upward Magnus force, just like for a pitch ball, and that makes the ball stay in the air longer. And basically, you're partially defeating gravity. So a ball will travel farther as a result. At least a ball hit at not too steep an angle. If you hit it too steep an angle, it'll do funny things, okay? It'll stay in the air longer so the fielder can get under it, okay? And that's not a desirable thing. But if you hit a ball on a fairly low trajectory, like 30 degrees or so, 25 to 35 degrees, backspin is good. It keeps the ball in the air longer and the ball will travel farther. So just like backspin makes the ball not really rise, but not drop as much as it would if it were just under the influence of gravity, topspin does the opposite. And a curveball is usually thrown with topspin. Not usually. A curveball is thrown with topspin. So they talk about a 12-6 curveball. Barry Zito has a good 12-6 curveball when it's working. And you see then you have a downward Magnus force, which goes in the same direction as gravity. And so that ball will drop more than it would just under the effect of gravity alone. And that's what a curveball does. As a matter of fact, if you really want to fool a batter, having it break sideways, just means you're not getting the good wood on the bat, okay? But having it break up and down, you see that you've got a whole lot less to play with here, okay? So if you can make the batter swing, under the ball for a rising fastball or over the ball, for a dropping curveball, you can more easily get a strikeout that way, or more easily get in the swing and miss. Balls that are hit above the center of gravity of the ball tend to have top spin on them, and if you hit a line drive with top spin on it, that tends to fall fall more rapidly than it would under the influence of gravity alone, and that's a good way to hit the ball, in the gap, or to get a single to the outfield, is to top the ball, because you don't want it to, if it's a line drive, sort of a low trajectory, you want it to drop as quickly as possible so that the fielder can't catch up with it. So you want it to hit the ground before the fielder gets it. And of course, there are all manner of breaking pitches due to the spin of the ball. Curveballs, sliders, cutters, these are all, the physics behind them, except for the knuckleball, are all identical. It's just how the pitcher grips the ball and the amount of spin and the axis of the spin, and that determines which way it breaks. Does the fastball rise? I've already mentioned that. Okay. Pitch FX. So Susan mentioned Pitch FX. Anyone here ever heard of Pitch FX? Some real baseball fans here. Okay. Okay. So Pitch FX. So if you watch a game on ESPN, they have this thing called the K Zone. If you watch it on Fox, they have a Fox Track, or I guess it's called Fox Track. Pitch FX. So if you watch MLB Game Day, you see screens like this that tell you how much the ball broke and the trajectory of the pitch. And these aren't just cartoons that people are making up. This is real stuff here, okay? These are computer rendered trajectories based on measurements of the actual trajectory. So the Pitch FX system, it's a joint venture of Sport Vision, a company, and Major League Baseball Advanced Media. That's sort of the media arm of Major League Baseball. BAM, everyone calls it. Okay? And how does it work? The Pitch FX system is installed in every Major League stadium as of the beginning of last season, the 2008 season. There are 2 video cameras that track the ball in 60th of a second intervals. And so here's an example. This is not the video, of course. This is just a still, but it shows you the ball in its trajectory in 1/60th of a second intervals. And of course, you need 2 cameras. You need to sort of triangulate, okay? One camera, you can't get 3-dimensional information from one camera, so you need 2 cameras. Typically, you want their line of sights to be as perpendicular to each other as possible. So usually there's one camera high above home plate looking down, and another camera on the first base side high above looking down, okay? And so they have fancy software to automatically find the pixel location of the ball in each image, and then they quickly do some crunching with the computer and tell you the exact trajectory. And so for baseball fans, this has been, I should point out, the data from this are all online, all free for the world to see, to download, to do with what you want, okay? And you just have to know how to do it. If you want to know how to do it, go to my website, and there's a link that tells you how to do all that. There's no secrets. And so people have figured out, and people use this for doing all sorts of things, mostly baseball analysis, looking at what pitchers, for example, since you have the full trajectory, you can figure out how much the ball broke. You can figure out how fast it went. You could figure out how much it broke, up, down, left, right, okay? Lots of different things. I'll show you some examples in just a second. Here's an example right now. So this is a pitch. John Lester pitches for the Red Sox. This is a game he pitched in August of 2007. I think it was against Seattle. What I'm plotting here is the horizontal movement on the pitch, how much it broke in the horizontal direction versus how much it broke on the vertical direction. So each pitch represents a point on this plot. So if the pitch wouldn't break at all, okay, it would fall in the middle of this plot. And when you make a plot like this, people discovered early on that the different types of pitches that a pitcher will throw fall into nice, neat clusters on this plot. So, for example, this is a 4-seam fastball. It's got it breaks upward. Remember, this is not This doesn't tell you where the pitch ended up. It tells you how much it broke relative to a pitch thrown with no spin on it, acting only under the influence of gravity. So this one breaks up, and Lester is a left-handed pitcher, and so his four-seam fastball has a little bit of a tailing action. It breaks horizontally into a left-handed batter. So this is the catcher's point of view. So a left-handed batter would be on this side, a right-handed batter would be on that side. So this has a little bit of a tailing action, so he throws it with a little bit of side spin. This is his two-seam fastball. It has about the same total amount of break, but a little bit less backspin, so it doesn't go up as much on this plot, but more side spin to it. This is his curveball. The curveball is the easiest pitch to identify because it's pretty much the only one that gives you a negative break in the vertical direction because it has top spin on it. And so now this is, again, thrown by a left-handed pitcher. It goes away from a left-handed batter towards a right-handed batter. And this is something like a cutter or a slider. And what's a cutter and what's a slider is a question of degree, how fast it's thrown. But they both are doing more or less the same thing. And I'm not sure I can easily distinguish the two. But it's an example of the kinds of things people study with this. Brandon Webb plays for the Arizona Diamondbacks. Here's Lester's little clusters. Here's Brandon Webb. Brandon Webb is a sinker ball pitcher. Okay, look, he's a right-handed pitcher, so everything is reversed, left and right. But here are his fastballs. Okay, his fastballs have an upward break. I get this line in the wrong place. Of only about 3 inches. Lester's are about 11 inches. Okay, so this is a classic example of a sinker ball pitcher. So a sinker ball is thrown I'm not sure exactly how the pitcher does it, but with a lot less backspin on it than it would for normal pitches. And as a result, the ball doesn't have that upward hop to it, so it falls more or less under the influence of gravity, which is more than a batter expects from a typical fastball. Okay. C.C. Sabathia, who pitched today, actually, if I recall, for the Yankees. But this was 2 teams ago. Okay, this was when he played for Cleveland. And people talk about late break on a pitch. Here is a trajectory of 2 different pitches that C.C. Sabathia throws. He's a left-handed pitcher and a very good one. The blue curve is his 95-mile-per-hour fastball. The red curve is his 82-mile-an-hour slider, and this is sort of a side view, an elevation view. It's remarkable that these 2 pitches look almost identical until you get about 20 feet from home plate. And then the slider looks like it just drops, okay? Now, it's a smooth trajectory. And in fact, if you follow it carefully, you see there's about a 4-inch difference between them back here. That's a little bit harder for the batter to perceive. If the batter is expecting a fastball, he looks at that, and it kind of looks like the fastball, and then the bottom seems to drop out of it at the last minute. It's a perfectly smooth trajectory from a physics point of view, okay? And, this is a classic example of a pitcher trying to make every pitch look like every other pitch for as long as possible. That's the way a pitcher fools a batter. So there's an old adage, Warren Spahn. Anyone remember the name Warren Spahn? Great left-handed pitcher. Warren Spahn said, batting is timing, pitching is upsetting timing. And this is a great example of it here. Okay, well look, I want to one more last thing, and then I'm going to sort of jump to the end. Tim Wakefield, he also pitched today in the day game of a day-night doubleheader for the Red Sox. Here's C.C. Sabathia's clusters, his fastball, his changeup, his slider cluster. Here's Tim Wakefield. Tim Wakefield throws a fastball, sometimes, not much, a curveball, even less often, and then he throws a knuckleball. A knuckleball defies everything I've told you so far. Okay, notice that the knuckleball is all over the place in terms of how much it breaks. It is all over the place. It's a truly chaotic system. It depends on the initial conditions and how the seam is oriented. And since there's an infinite variety of initial conditions, you see there's an infinite variety of ways it can break. Now, what happens? So a guy by the name of John Walsh, who's a high-energy physicist who lives in Italy, actually, did this analysis last year. I thought it was a cute analysis. Sorry, this didn't show up quite well. What happens when a knuckleball doesn't knuckle? So what I'm showing, so here is a color-coded thing. The red blotch in the middle there are knuckleballs that basically are not breaking very much, and then the green breaks a little bit more, and the blue are the ones that are really effective. If you look at what is known as the OPS, it's the on-base percentage plus slugging percentage, it's a measure of, a batter's effectiveness. For the outer band of blue, it's 684, a relatively known number. And notice that it gets bigger and bigger. It's 979 here. So this is an interesting analysis. It shows when you throw a knuckleball and it doesn't do the movement that you want it to do, it ends up in the middle of this plot, people are whacking it. And, of course, we know that happens, okay? But it's kind of nice to see an analysis that shows that, too. All right, what's the deal? Okay, I want to jump to the end because I'm running out of time. And we can talk about this later if you like. Things I'd like to know better about aerodynamics. All right. So work in progress. I continue to do collision experiments with colleagues, people who have facilities that allow me to do them, to try to study this trampoline effect that I told you about, which I find totally, completely fascinating. New studies of aerodynamics, high-speed collisions more, to quantify the spin of the ball. And I'm working on a book with an Australian guy who's mostly interested in tennis, but he's also gotten interested in baseball a little bit. All right, so final summary. Physics of baseball is a fun application of some basic physics and some not so basic, the stuff that's harder than rocket science physics. Check out my website if you want to know more. Feel free to send me an email. I get emails all the time, and I have one rule, which is I always answer them. Maybe not always immediately, but I always answer them. And I'm living proof that knowing the physics doesn't help you play the game any better. And that's me. At the Red Sox Fantasy Camp, February 1 through 7. And I was playing first base here, and I was getting ready to hit a ball here, and studying the physics of baseball didn't help, I can tell you. Thank you very much.